In this video, we'll be going over rolling motion. So what is rolling motion? So rolling motion is when an object translates, which means that its center of mass moves, and also that's when the object rotates, which means it spins about its center. And also these are the three conditions: 1, 2, and 3. It does not slip at the points of contact. Moves for this is for rolling motion. So the defining condition is that the v center of mass is equal to the angular velocity times the radius. And at this point, the points of contact with the ground is instantaneously at rest. So now let's talk about the difference between, so again, we know that the difference between translational and rotational motion is that translational is the motion of the center of mass, and then the rotational motion is the spinning around the center of mass. So, and also the total kinetic energy of a rolling object, that's going to be K total, is equal to 1/2 of m v squared plus 1/2 of I times the angular velocity squared. And using the rolling equation, v is equal to omega times r, this can entirely be rewritten in form of v. But so for this, for our purposes today, what you really need to know are the inertias for these three shapes. So a solid disk slash a solid cylinder, and also a solid sphere. So respectively, that is the inertia of I is equal to mr squared, I is equal to 1/2 mr squared, and I is equal to 2/5 mr squared. And basically the thing you can take away from this is that objects with a larger moment of inertia roll slowly down a ramp. Now let's continue with what is the role of friction in rolling. So in rolling, we have to know that static friction, it does no work. It also does not dissipate energy. And it's also essential for enforcing V is equal to WR. And let's do some practice problems that show these. So let's say we have a solid cylinder of mass m and radius r that rolls down without slipping a height of a ramp of h. Find its speed at the bottom. So first you have to identify the energy conservation. So there is energy conservation, and why is this? Well, that's because there is no slipping. So that means mechanical energy is conserved. So that means you can write out your energy initial is equal to the energy final, and in the beginning you all have potential energy, and then in the end you have kinetic energy, and kinetic energy, which is more specific, kinetic energy translational, plus your kinetic energy rotational. Imagine this: you have your ramp up here, you have the cylinder of mass m, and so let's actually draw a cylinder up here. So you have a cylinder like this. That's your cylinder. So cylinder up here, cylinder down here. up here you only have potential energy, and then down here you have kinetic energy. But then when you're up here, the potential, you have all translational. But then when it rolls like this, some of it's being rolled, so then it becomes translational plus rotational down here in the bottom. So now you can replace this with the formulas. Potential energy is mgh, and then kinetic energy is 1/2 mv squared plus 1/2 I omega squared. Now we want to substitute in the moment of inertia. Oh, my bad for that. The moment of inertia is I, which is equal to 1/2 mr squared. So now we have that mgh is going to equal to 1/2 mv squared plus 1/2 of the moment of inertia here squared, times omega squared. And now we can use the rolling condition, which is that omega is equal to v over r. Now from here, we plug this into here. Let's get your green, and then you have mgh is equal to 1/2 of mv squared plus 1/4 mv, what color? Well, yeah, mv squared. And that's because, well, if you want to see the substitution for this, that's gonna be, well, we should actually do it up here. The substitution for this was here, vr squared. So you would see that v squared, and then you had r squared. So r squared would have canceled out, and you just be left with v squared. So after this, you have just mgh is equal to 3/4 mv squared, and then you just take the root of both sides. Then you have that v is just equal to the root, is equal to the root of 4gh over 3. That is your velocity. Now let's move on to our second problem, which is which object reaches the bottom first. So imagine you have a hoop, a solid disk, and a solid sphere that roll down an identical ramp from rest. Sorry about that. So now you need to use the formula for the general rolling results. And this formula is gonna be v is equal to the root of 2gh divided by 1 plus I divided by mr squared. And what you have to do is you need to compare specifically I over mr squared, this component right here, and you need to find this of each object. So for a hoop, a disc, and also a sphere, so that is going to be 1, this is going to be 1/2, and this is going to be 2/5. And that was basically the number that we had up here. That was like the number that was like right in front. So kind of correspond there. So I mean, they're all the same. Mr squared, it's just scaled by something, right? So what we know is that if you have a smaller denominator, that means you have a larger acceleration. Therefore, if you have a larger acceleration, it arrives first. Again, acceleration is equal to the change in velocity over time, and velocity is equal to the change in displacement over time. So if something moves to x, point x and point z faster, that means that it gets there first. So your final ranking is going to be 1, the solid sphere, 2, the solid disc, and 3, the hoop, in accordance of their sizes of their denominators. The sphere is the largest, the solid's disk, the disk is gonna be second, and then the hoop is gonna be last because you want a smaller denominator. Now let's move on to this question about rolling with given speed. So let's say we have a wheel of radius 0.30 meters. So r is equal to 0.30 meters, and it rolls without slipping at 6.0 meters per second. So we want to find the angular speed first. So see, this is our first part of the question, angular speed. So that's going to be omega is equal to v divided by r. That's going to be equal to 6.0 divided by 0.30, and that's going to equal to 20 rad per second. Now let's find the angular displacement over 5.0 meters. So that's going to be theta is equal to s over r. That's going to be equal to 5.0 divided by 0.30. That's going to be approximately 16.7 rad. Now let's do a question about the number of revs. So n is going to, the number of revs is going to be theta over 2 pi. So theta is going to be like the angle, right? And 2 pi, we know there's 2 pi in one circle. So that's approximately 2.66 rev. So again, rolling condition is V equals omega times R. Total kinetic energy is translational plus rotational. Energy conservation is, let's see here. Write a note that energy conservation is valid if there's no slipping. Friction is also static, and faster rolling equals a smaller moment of inertia. Now let's move on to another question. A solid sphere versus a hollow sphere. A solid sphere and a hollow thin sphere of equal mass and radius roll without slipping down identical ramps from the same height. Which one reaches the bottom first? So you have this, we have first a sphere that is gonna be here, and then we have second sphere. So solid, we're gonna label this solid, and this is gonna be the hollow one. So which one's gonna reach the bottom first? Well, first we can use energy conservation. We have that E initial is gonna equal to EF, because up here, potential energy, kinetic energy, and also they're gonna roll. Therefore, this is gonna be kinetic energy plus kinetic energy. It's gonna be potential energy translational here. Final energy here. So therefore we can plug in mgh is equal to 1/2 m v squared plus 1/2 I times omega squared, and now we can use v is equal to omega times r, our slipping condition. So because of this, now we can also substitute in our moment of inertia. So for the solid sphere and also for the hollow sphere, you have I is equal to 2/5 mr squared, and then you have I is equal to 2/3 mr squared. Now you want to solve for the solid sphere. So that's going to be mgh is equal to 1/2 of mv squared plus 1/2 2/5 m r squared times v over r squared. So that's going to be mgh is equal to 1/2 mv squared plus 1 over 5 mv squared, and that's going to be equal to 7 over 10 mv squared. Again, this is mgh. Now you just want to take the root of both sides, but first let's actually multiply this by 10 over 7 and divide that by m. So here you have 10 over 7 divided by m. Mass will cancel out. Okay, it's not turning into red. Mass will cancel out. Everything here, that will all cancel out. So now you just have that the velocities is going to equal to 10 times gravity times the height divided by 7, square root of that. And yeah, that's going to be the velocity. And now for that was just for the solid sphere. It's for the solid sphere. Let me save equation. Now for the hollow sphere, on the other hand, we have, it's the same thing, just plug in the different. MGH is 1/2 of mv squared plus 1/2 2 over that mr squared times v over r. Might as well just make that green too. Make this orange as well. So this is going to be equal to 1/2 of v squared plus 1 over 3 v squared. That's going to equal to 5 over 6 v squared. Now this is going to be equal. Now, okay, we just want v, right? So that's 6 over 5 times 6 over 5 times m. All right. So let's cancel out. Let's take the root of both sides. Right, so then you're just gonna have v is equal to the square root of 6gh over 5. Now, this one reaches the bottom first, and those are the final velocities for both of them. So now let's do another problem. Rolling object with a known acceleration. A solid cylinder rolls down without slipping at an incline angle theta. Now we want to find the acceleration of the center of mass. So what forces can we draw around the cylinder? So let's say that the cylinder looks like this. And you want the center of mass. So the forces that are acting along the incline, that's going to be mg sine theta minus f is equal to ma. So I've added some labels on the inclined plane. So as you can see here, we have the normal force that's pointing up, and that's going to be the weight times cosine theta. And first let's talk about the weight. So weight is going to equal to the mass times the force of gravity, the acceleration of gravity, which is down. And then if you split that up into the components, the vertical and the horizontal components, we get w sine theta, which is the opposite over hypotenuse. Opposite over hypotenuse for the ratio of this theta right there. And here we get w is equal to cosine theta by getting the adjacent over the hypotenuse over here. And then we can, everywhere we see weight is equal to mg, we replace that, and then we get mg cosine theta here. But we know that that the summation of the vertical forces equals to 0 because there's only it's going down the ramp, not through the ramp. So there's nothing that's like causing it to go through. It's mainly the horizontal motion. That's because the normal force is keeping it on top of the incline and not like going through the incline. So, and we also know that this mg sine theta is going to be greater than the frictional force because it has to overcome it in order to slide down the ramp. So, and why is there friction in the first place? Well, because friction is the force that makes the cylinder rotate. This frictional force, it makes the cylinder rotate. And so we know this is because if the incline was frictionless, then the cylinder would just slide down without spinning. So essentially, remember that friction is the thing that perpetuates. It allows something to roll, to spin. And the lever arm is also, we can elaborate this. Talking about it's the lever arm R. And we also know that friction, again, it acts as the point of contact on the rim of the cylinder. And this is exactly 1 radius away from the center of mass. So from this, we can deduce that the torque is equal to the force times the radius. And we also know that the inertia for a solid cylinder, no, actually I want to change this color to a different color. Make this blue. So for a solid cylinder, the moment of inertia is I is equal to 1/2 of mr squared. And we also know we have to know the angular acceleration. So this is the angular acceleration, which is alpha. This is how quickly the spin speed is increasing. So in rolling without slipping problems, it's actually the bridge between linear and acceleration and angular acceleration. So that's the formula. Alpha is equal to the acceleration over r. So now from this, what we can do is, this was from A is equal to alpha over r. And now we can substitute this alpha into here. So let's make that more of a. So we also have the identity that the torque equation about the center, that is Fr, is equal to the moment of inertia times the angular acceleration. So we saw that's the angular acceleration. So now we also see that this is I, and now down here we have that Fr is equal to the 1/2 mr squared times the A over r, and that is going to give us that's AR. Yeah, so I have F is equal to 1/2 of MA, because the r squared, yeah, so you have to divide that by r. So you multiply it by r down here. So that's means 2 r's. That cancels out. And now we have to substitute. So we can just call this equation 2. And we have our force equation, which is this. So we have to sub 2 into 1. 1 was this. So now what you're going to do is you have F. Why don't we make this, let's make it purple. So now we're going to have, that was F. So this would be right there. can make that purple to show that we plugged in there. And you're going to have just mg sine of theta is equal to 3 over 2, because this is basically 2 over 2. You add 1/2. And now solving for just the acceleration is going to be 2 over 3 g sine of theta. And to prove that, this is 2, and that's going to be 2 over 3 times 2 over 3 divided by m, and that cancels out, and that is your answer. Now let's do question this. So a wheel rolls without slipping up an incline. So now we're going up an incline, not down. What direction is the static friction, and does this friction work? So for A, let's start off with, so as the wheel goes upward, gravity reduces translational speed. Without friction, rotation wouldn't decrease properly. So therefore, static friction must act up the incline to reduce the angular speed. And you might be wondering that usually we know that friction opposes motion, right? So you might be wondering, why is it acting up if the motion is going up as well? Well, that's because that this is rolling without slipping. If it's rolling without slipping, that means that one of the things that we have is that friction, it acts to prevent surfaces from sliding against each other. So there's a conflict of motion, because as the wheel rolls upward, the gravity is pulling down on the center of mass. So the center of mass, we have gravity pulling down, and that what Fg does, it reduces the translational speed. But since gravity is acting up at the center, so the translational speed, but it acts at the center, so it doesn't provide torque to slow down the rotation, no velocity omega. And that's because it's right on the axis. This is the center of mass, so that's the axis of rotation of the ball, the sphere. So because there's no distance from the sphere and there's no theta from the sphere, like, it's just gonna be no torque. So that means that and also, like, you can think that if there were no friction, the wheel's forward speed would drop quickly due to gravity. But it would keep spinning fast. Or keep spinning in place, which is like spinning its wheels, because rotation wouldn't No, it needs to slow down to match the slower forward speed. So because we have friction though, to maintain the rolling without slipping condition, which is v is equal to r times omega, the angular speed, okay, yeah, so omega must to maintain must decrease at the same rate as translational. So to reduce, so how do we reduce each of these? Well, this is reduced using torque, and this is reduced using force. So you need torque to oppose your current rotation. So because the wheel is because we know that it's going up the hill, it's currently going counterclockwise because it's going up the hill. It's being pushed like this way. So, but we like need it. But for torque, we want the torque to oppose the current rotation. So for our required torque, it has to go clockwise. So therefore, friction, we know friction, or more specifically static friction, must act up the incline to the right to provide that clockwise torque at the contact point. So it will reduce the angular speed. Now let's move on to B. Does friction do work? Well, static friction does no work because the point of contact is instantaneously at rest. And the reason for this is we have to look back at the definition of work. So work in a mechanical system, work is done when a force is applied over a displacement. So work is W equals to FD cosine theta in the translational world. Now let's think about the no slip condition. So when a wheel rolls without slipping, the point of the wheel currently in contact with the incline is instantaneously at rest. And what does this mean? This is kind of like a confusing thing, right? So, well, it's not, once I explain it. So it's static, not kinetic. So that means that because there's no sliding, it's rolling. Sliding, we have static friction. And that means that so we have zero displacement, because if it's not sliding, then we have no displacement because there's no reference point. So at the exact moment that the static friction force acts on a specific atom of the tire, the atom is not moving relative to the ground. So the exact moment the Fs So there's a handoff of this. As the wheel moves, as the wheel moves, a new point of contact is established, and the previous one lifts off the ground. At no point does a single contact point drag across the surface because it's constantly changing. So because the work done by static friction is equal to 0, therefore no mechanical energy is lost or converted to heat. That's why we can use the conservation of mechanical energy. Conservation of E for rolling. So now let's continue with our next problem. A solid disk rolls without slipping into a vertical loop of radius r. What is the minimum speed at the bottom so it just maintains contact at the top? So here's a little diagram to represent what we're trying to tackle. You can see the disk is moving in a vertical cylinder, a vertical circular motion, and at the top it's going to be having a speed of v squared equal to g times r, and the total energy is going to be equal to the kinetic energy translational, kinetic energy rotational, and potential energy. And then at the bottom it's gonna have no potential energy and translational and rotational kinetic energies. The change in height is just 2r. So now what we can do, the way that this was at the top was derived is that you had mv squared over r, because Fn is equal to 0, is equal to mg, and that gives us v squared is equal to 2gr, because m cancels out. Now using energy conservation, we know that the bottom to top height is equal to 2r. So this was our total energy. But let's focus on. So we have 1/2 mv initial squared plus 1/2 IWO squared is equal to mg times 2r plus 1/2 mv squared plus 1/2 inertia times omega squared. Now we can substitute I is equal to 1/2 m r squared for a solid disk, and we also have our slipping condition of VR. So substituting that in, we have 1/2 mvo squared plus 1/4 mvo squared is equal to 2 mgr plus 1/2 mgr plus 1/4 mgr. That's going to be equal to 3/4 mvo squared. It's equal to 11/4 mgr. What do we want? We just want to isolate just that. So we are going to multiply both sides by 4/3. And that's going to cancel the 4's out. And you're also going to multiply and also now we're going to take the root of both sides. Now that's going to cancel out this mass right there, and that's going to leave us with the v initial is equal to 11/3 times g times r, and that is our solution. So to elaborate a little bit more on this, the energy at the top, well, we know that the energy at the top is equal to the bottom. I can write that there. To be a little bit more in details about how we got V is equal to the root of GR as the speed at the top, well, we know that the net of the forces is equal to the normal force plus mg. And we know that that is going to be equal to mv squared over r because this is centripetal motion and it's pointing towards the center of the circle because of gravity pointing down and normal force pointing up. So we have Fn and we have Fg. And we also have the mass as well. And from here, we know that the normal force is equal to 0. And the reason why is because to find the minimum speed required to remain on the track, we look for the moment where the disk is just about to lose contact, which is at the top. And then at this threshold, the track is no longer pushing on the disk, so the normal force is equal to 0. So therefore, at this specific speed, the gravity alone acts as the centripetal force. So then the masses cancel out, then you just get v squared over r is equal to g. So then you just rearrange, you just have v squared is equal to gr, and then you just get take the root of both sides, you get v is equal to gr, root of gr. And yes, now let's move on to let's see, did we do, okay, did we have anything? Oh, okay, so it's just, let's do 5. So let's see here. A horizontal force is applied to the top of a rolling wheel. Does the wheel accelerate faster, slower, or the same amount compared to pulling at the center? Let us visualize this. We have a horizontal force applied to the top of the wheel. So that means that it's tangential. Because we can imagine that like here, that will be 90 degrees. So at the top, that means we have a pull. It produces a translational force and also produces a torque in same direction as rolling. But let's say we pull in the center. Well, this pull produces no torque directly. Because it's right there on the center of mass. Pulling at the top makes it faster because there is distance, there is r, and due to the torque. So again, here we have this radius. So we have this radius, and because of that, we have torque. So we have Fa, and we also have torque in the same direction. And but when you push in the center, that you only have Fa, because you're pushing the force on the pivot point, which is the center, and that makes the lever arm equal to 0 because the radius is equal to 0. So there's no assistance of helping the wheel spin by pushing there. So again, so Fa plus torque at the top contributes to the rotation, but when you push in the center, only Fa contributes to the rotation. Now, but you have to note that if there was no friction, if you push the wheel in the center on a perfectly frictionless surface, like smooth ice, then the intuition of pushing like there would mean that it would slide without slipping at all, because there would be no friction to provide a grip at the bottom. There would be no instantaneous like point of no displacement. So that means there's no torque to start the rotation. Therefore, there is no rotation. Therefore, no rotation. It's just gonna slide like a box. That would not occur unless it was ice. Now, let's calculate the linear acceleration for both cases using Newton's second law for translation. Now, we can use F is equal to ma. And rotation, we have IA for trans and rotational. Now at the center, we know that we have, for translational, we have F minus F times ma, and then we have for rotational, we have that FR is equal to I times A. I is going to equal to 1/2 mr squared, and alpha is equal to A over R. And the friction required, is 1/2 ma. And then plugging this back into the translational equation right there, we can actually, let me just make this. We have that F is equal to F minus 1/2 ma is equal to ma. F is going to equal to 3 over 2 ma, because this is just 2 over 2 ma. Therefore, the A center is just equal to 2F over 3m. That's because you have 2 over 3. Now, on the top, we have that translation. When you push at the top, both your force and your friction, they both act at distance r from the center, and that creates a combined torque. So then translationally, you have F plus F is equal to m times the angular acceleration, and friction. Here's an important note that we should write down. Friction usually points forward at the top here to help rotation. But let's actually put this at the top so that we translational, so relates to here. Now for rotational, we have F minus F times R is equal to inertia times alpha. So now using the same substitutions that we did for I and A that we did down here, we have F minus F is equal to one of those R's cancel. So therefore, you can add the translational plus rotational to eliminate. Okay. F, so then you have 2F is equal to 3 over 2M. A, so then the A at the top is equal to 4F divided by 3M. So now we can see that pushing at the top is going to be 4F, and then the bottom is going to be 2 over 3. So this is basically double the acceleration. So pushing at the top is more efficient because it contributes to the rotation directly rather than forcing the ground to do all the work through friction. So now let's go to our last question. A disc is initially slipping without rotating on a rotational surface. Eventually, it begins rolling without slipping. Is mechanical energy conserved during the transition? No. Kinetic energy does work while slipping occurs. B. What enforces the rolling condition? V is equal to omega R. Energy is not conserved during slipping, and also static friction is what enforces the rolling. Alright, thanks for watching.